All right, well, this is CS50, and this is lecture 4. And you'll recall that last time we focused really on algorithms, not so much code, but on algorithms, these step-by-step instructions for solving problems. And we did this in the context of numbers, but more specifically, we assumed that we had places to put these numbers. We called it an array, and that was back-to-back-to-back memory, where we could put numbers or maybe characters or something else. But for the most part, we haven't really had more sophisticated ways of laying information out in memory. And so we're kind of stuck going left to right, right to left, or maybe a little more intelligently, using what we've called binary search, or divide and conquer, and kind of split the difference. But we can start to get fancier, because if you recall, we have memory inside of our computers, which we keep modeling as this rectangular region with numbers and so forth. But that's kind of a nice canvas, right? Much like you could paint on a canvas, so could we kind of move things around in memory, but we don't yet have the vocabulary or really the data structures, as they're going to be called, to do anything more interesting than this linear approach. And so today and next time, will we begin to start to solve problems more cleverly, and then revisit some of the kinds of algorithms that we've seen already. And those algorithms last time were like these, linear search and binary search. And that brought us full circle back to week 0 when we used those, albeit not by name. And then recall that we introduced sorting. Sorting is a more involved algorithm, more time-consuming, but it was a precondition for which of those first two algorithms to actually work. Yeah, so binary search assumes, just like a phone book assumes, that the names are actually sorted from left to right. Otherwise, you're completely wasting your time if you're splitting a phone book in half if there's no rhyme or reason to where the names and the numbers are. So this is sort of a requisite ingredient to get better efficiency with other algorithms, and we're going to see that moving forward. And it's going to be up to decide, you know what, it's going to take me more time to figure out how to write the code for an algorithm than it is to just write it the easy way and just cut a corner and run the code once. But if you're a company, if you're a website, if you're a piece of software that's doing the same algorithm again and again and again, maybe you do want to spend that upfront cost. Maybe it's human time, like your time figuring out the algorithm, or maybe it's n squared, or hopefully something better, n log n, that you have to spend just to get the data in a nice format, and then thereafter everything can be blazing fast. So especially when we get to web programming, we'll revisit these questions when we talk about databases as well. But recall last time we also introduced a bit of formalism, and we won't get more mathematical than this, but these were sort of broad strokes with which we can paint the efficiency of algorithms, from sort of slowest on top to fastest on the bottom. And recall that we introduced some Greek symbols here just to kind of standardize what it is we're talking about. And as a quick check, big O refers to what kind of boundary? The upper bound. So maybe in the worst case, what's the upper bound on your algorithm's running time? How many steps, how many seconds, how many hours might it take? By contrast, we had omega, which was lower bound. And then less commonly used, at least in CS50, will be theta, which is just when those two are the same. But realize those are the three ingredients, especially if you continue on in other CS classes that might be revisited. And we introduced this so that we're not just counting seconds. We're not like looking at our watch and counting how fast our algorithm is, because that's not a very reliable way of measuring whose algorithm is better than someone else's. Maybe my Mac is faster than your Mac or your PC. And so we don't want to just look at raw time. We want to think about things a little more theoretically, albeit without worrying about denominators and lower ordered terms. We talk generally in terms of these highest order terms that we saw last time. So I thought it would be fun to kind of reminisce some years ago when a certain someone was still just a senator being interviewed by Google's own Eric Schmidt, who was the former CEO of Google. And this was an interview that took an interesting algorithmic turn. If we could dim the lights for a moment.
Now, Senator, you're here at Google, and I like to think of the presidency as a job interview. Now, it's hard to get a job as president.
Right.
And I mean, you're going through the rigors now. It's also hard to get a job at Google.
Right.
We have questions, and we ask our candidates questions. And this one is from Larry Schwimmer.
Okay.
What? You guys think I'm kidding? It's right here. What is the most efficient way to sort 1,000,000 32-bit integers?
Well,
I'm sorry. Maybe
no. I think
that's not a.
I think the bubble sort would be the wrong way to go.
Come on, who told him this?
OK. So today we peel back the layers that we've been assuming for some time now. We've been talking about integers and characters, but we also had this like higher level concept of a string, which was a generic way of saying you had back-to-back characters that represent words or sentences or paragraphs or whatnot. But today we reveal that that's actually been a bit of a lie. Like there actually is no such thing as string in the language called C. And indeed, you might have kind of suspected as much, given that we keep including CS50.h, which gives you things like getInt and getString and so forth. But it also gives you string, literally, a key word that actually doesn't come with C. And before we peel back what exactly it is, let's consider perhaps what it is that what problems it creates and what powers it reveals to understand what's going on underneath the hood. And let me propose that we try to implement, at least in pseudocode, this algorithm here, swap. So I proclaim that swap is a function whose purpose in life is to take two inputs, let's call it A and B, and just swap them so that A becomes B and B becomes A. And before we even get into the weeds of pseudocode or actual code, we actually have two values here. Might anyone like to join me on stage for just a moment for a drink of Gatorade? A little Gatorade, maybe someone a little farther back today? Little drink, yeah? OK, come on down. What's your name? Kate, come on down. Join me for some Gatorade on stage. Welcome to Kate. All right. So the challenge at hand is this. Let me just set us up here. So we have some green. Very unnatural looking. OK, we have some pink. And you know what? I think actually I'd like the pink, and maybe you could have the green. I need you to swap the values of these two cups, if you could. I need you to get the pink into the green cup and the green into the pink cup. OK, hey, so she thinks she's going to need another cup. And OK, so good, I came prepared. So we need another variable, if you will. OK, so here we go. Kate, set us up. All right, green goes into the empty cup. All right, so pink goes into the former green cup, and most green goes back into the original cup. Thank you so much to Kate. Why don't we, I don't know if you'd like that flavor. Delicious. OK, well, thank you very much. Thanks for coming up. Here we go. And this. Oh, and if you'd like. OK. So this was obviously very intuitive. That one's not bad. This is actually pretty intuitive, of course, for any of us in the room, that you obviously can't very cleanly like swap two values or two drinks. You need some kind of temporary storage place. And so we can introduce this in the form now of some actual code by claiming that if you want to swap two values, you need the exact same idea. So even if variables have seemed a little abstract, or you're at least used to them in the context of algebra, x and y, in a programming language, variables are just like these empty cups into which you can put values. In reality, it's green and pink, but it could be a number, it could be a letter, or maybe something more, maybe even something like a string. So we're going to come back to this idea, because if you agree that Kate's algorithm was correct once she had that temporary variable, it would seem that this is a pretty reasonable translation to code. Store A in temp. So move A into the temporary variable, just like she did into the empty cup. Then change A to be B. And then change B to be what was A, which is currently in temp. So it's kind of this three-step switcheroo, just like Kate enacted for us here. But recall last time that we have, actually, let's do this. Let me actually go ahead and open up a program here. You know what? Let me go ahead and open up, let's say, today's example called no swap, which is a bit of a spoiler, insofar as the name suggests what's actually going to or not going to happen here. And if I go ahead here and open this up in source 4, let me go ahead and open up no swap. Let's take a look at what this program actually looks like. It doesn't seem to do all that much, but it does have a main routine up front, and it's got an include of standard.io.h. And then what does main do? It declares two variables, this time called x and y, initializing them to 1 and 2 respectively, and then a couple of printfs. So printf x is such and such, y is such and such, printing out its actual values. So that's sort of week 1 use of printf. And then we do it looks like the exact same thing 2 lines later. But in between those 2 lines is an actual function call to something called swap, which, as it turns out, if we scroll down, is literally the same thing as we had on the screen a moment ago. I'm calling it A and B here, but I could have called it anything I want, x and y, foo and bar, anything like that. I have my temporary variable or temporary empty cup like Kate had, and I do the switcheroo. So when I run this program, after compiling it with Let me go into source 4 and then do make no swap, enter. Seems to compile OK. So when I run no swap, what sentences should I see on the screen based on main? Yeah, x is 1, comma, y is 2, and then hopefully x is 2, y is 1, if swap indeed works exactly as Kate enacted in the real world here. So as the name might suggest, doesn't seem like something's going to go quite right here. That's weird. Like, it didn't actually seem to swap the value. OK, so maybe it's a bug. Like, we've screwed up before. Maybe I just made some error. Maybe I'm kind of saying I'm doing one thing, but I'm actually doing another. So let's double check. So int x gets 1, y gets 2. That seems correct. My sentence is correct. It's x comma y, and then it's again x comma y. So I didn't accidentally reverse them. I'm printing the same thing. I'm calling swap. And so it seems Kate was wrong. Like, she did not swap the green and the pink Gatorade correctly somehow, because at least in code it's not working. So why is this? And it turns out that the answer to this, Kate's algorithm, is actually correct, but our interpretation of it in code isn't quite correct. Even though it compiles, even though it runs, and it actually is doing something underneath the hood, it's not actually obviously doing precisely what we want. So why is that? Well, let's come back to this picture here, which is just a stick of RAM that you might have in your desktop or your laptop. And each of those black chips has some number of bytes, maybe a gigabyte, maybe less, maybe more these days. And I keep proposing that we think of these, if you can just kind of zoom in, it's just a grid of values. So if we zoom in on that and we think of the top left corner as the byte 0, the one next to it byte 1, byte 2, we can literally number all the bytes in our computer from 0 to like 1 billion or 2 billion, however much RAM you actually have. But it turns out that computers use that memory not exactly as left to right, top to bottom. Like, there's a bit more structure to it. And so let's actually be a little more precise today and zoom in and propose this. There's a lot of words all up front, and we'll tease them apart in just a moment. But if you think of this as that black chip on your computer's memory stick, it turns out that the computer is going to use different areas of memory, the stuff down here, just a little bit differently conceptually. Humans years ago decided to use this memory for certain things, this memory for certain things, and we've all kind of standardized on that since, at least in C here. So there's going to be two salient features here, so-called the stack and the heap. And the heap we'll get to before long, but a stack is just like it is in English. Like if you go over to Annenberg or some dining hall on campus, you just have a stack of plastic trays. That's the same idea, we'll see, where you can put more and more stuff on the stack, and the heap's going to work a little bit differently. But you can still think now, even though we've started to kind of label different parts of memory with these words, heap, stack, and others, you can still think of the idea as being exactly the same. Within the so-called heap portion of memory, we're still going to number our bytes, 0, 1, 2, 3, 4, much like I've proposed with some squares here. Same thing for the stack. The numbers might be different because they're obviously farther away from those other boxes, but we're still just going to number them. So the mindset is the same. It's just we're putting different types of things in different places starting today. And let's see what this means for us in reality. I'm going to go ahead here and create a new program called compare0.c. If you'd like to play along with at home, the same code will be online on the course's website. As usual, I'm going to do like an include of CS50.h. I'm going to do an include of standard.io.h. Then I'm going to do int main void. I'm not going to worry about command line arguments today. And then I'm going to go ahead and get myself two strings. So I'm going to do string s, we'll call it. Get string, and I'm just going to call this s. So I'm going to prompt the user with a pretty simple string, like just give me s. I want one more. String t gets get string, t colon, and then a double quote. So just sort of, again, week one stuff. Just give me one string, then give me another string, and put them in s and t respectively. And now let me just do something that you might have been inclined to do or had to do previously, which is just to compare these things. So you know what? I want to check. If the user typed in the same word twice, let me just say if s equals t, I'm going to go ahead and print out, quote unquote, same, and a new line. Else, I'm going to go ahead and just literally print out different. So I've whipped up a simple program that I think is just going to ask the user for two strings and then just compare them. Now, in the past, I have made mistakes when it comes to equal signs. Have I used the correct number of equal signs for something like this? Or should it just be the 1? So it should be the 2, because the 1 is used already as assignment. Move this from right to left. So equals equals seems to have the right semantics. Like I'm trying to compare s and t for equality. So let me see. If I got no syntax errors here, let me go ahead and make Let me go ahead and make compare 0. OK, compiled. And then / compare 0, enter. Let me go ahead and I'll type in like Stelios' name again. I'm going to go ahead and type his name again. Looks good. Enter different. OK, maybe, I mean, it's kind of a long name. Maybe I just screwed up somehow. So let's try this again. So I'll type my own name twice. No, OK. Maybe we should try another, like Maria. Like 3 times incorrect. There's got to be something wrong with my code. So what is actually going on? Well, maybe we should just go about this a little differently. Let me go ahead and try another program. Let me go ahead and create a new program called copy0.c. And this time, you know, maybe comparing, I'm just going to copy the strings this time in order to actually do something simple and see the results. So let me go ahead and do an include of CS50.h, an include of standard.io.h, int main void. I'm not going to worry about command line arguments. And I'm going to again do string s gets string. And I'm just going to say give me s. And you know what, this time, rather than complicate things by getting a second string, let's just say t is going to equal s. So I think this is the correct use of equals, because it's 1 equals, which means copy s from the right to t on the left. All right, and then I'm going to do, I want to capitalize this string. So let me just insert a little bit of logic here. And I only want to capitalize the string if the user typed something in that's long enough. So I want to do a little bit of safety checks, because we're starting to get in the habit of better error checking now. So if the length of t is greater than 0, you know what I want to do? I want to go ahead and change the first letter of t, the copy, to be the result of calling toUpper of that first character of t. And then, you know what, let's just print it out. So s is going to be %s. And let me plug that value in. And then let me go ahead and print out t %s \n, comma t. So it's a bunch of syntax all at once. But to recap, I'm getting a string, calling it s, just like before. I'm not getting a second string. Now I'm just saying, you know what, the string called t is going to be equal to s. And we've used assignment certainly before. Just to be clear, why did I complicate my code with this use of Sterling here? Why did I do that? What could go wrong otherwise? Someone else? Propose to me what the user could do that might make problems for me. Yeah? Exactly. Suppose the user doesn't type his or her name and just hits like enter. That's going to return a string of 0 length. Now, technically, a string of 0 length uses up how many bytes in memory? Why 1? Right, there's still a \0. So recall last week when we talked about what strings are underneath the hood, they're always terminated by \0. Whether there are 0 characters, 1 characters, 5 characters, or 1,000, they end with a \0. So even if the user just types enter, he or she is really creating a string that's of 1 byte in memory, but its length, so far as we humans care, is 0, because there's no characters in it. But if you look at that 0th character, just to be clear, what is going to be at t_0 in this case? \0. And if you now change this to be toUpper, like, it's just weird. You shouldn't be touching that \0 and certainly not trying to capitalize it. So I'm being a little defensive here, though hopefully, frankly, toUpper would not break in that case because it's not an alphabetical letter. But I'm at least thinking about these circumstances. Now I'm just going to go ahead and print out both s and t. So let's see the result. So let me go ahead and make copy 0. And oh, OK, we've seen this before. Let me zoom in on the bottom. So the first error message here has something to do with implicitly declaring library functions. That's a pattern you should start recognizing now. What does that mean I probably omitted? Yeah, so some library, some header file up top, and maybe by instinct or maybe by running help 50, you would recall at this point that, oh, right, I need to do like include string.h. And just to anticipate, is there one other I should add before I embarrass myself with another error? Yeah, so include C-type. It's not so much an embarrassment. It's just I should know it once I've seen it once before. So here we have C-type because what's in C-type? toUpper, right? And we would only know that from like Caesar or Visionaire having done it before. Otherwise, you pick it up along the way. All right, so now let me go ahead and rerun make copy 0. Seems to work OK. Let me go ahead and do /copy 0. And let me type in Stelios' name, but all lowercase for s. Hit enter. OK, kind of worked. But what's the symptom here now. Yeah. Yeah, capitalize both S and T, but maybe this is like a screen thing, like lowercase s and capital S kind of look the same anyway, so maybe we're just kind of seeing things. So let me just type my name in lowercase, where the D is hopefully going to look quite different. No, same behavior. So why is this? What's going on? Again, the code here is just an application of the ideas we've been using for the past couple of weeks. If you want to get a string, call getString. If you want to copy a variable, use the assignment operator from right to left. And so here is where we're beginning to find weaknesses or sort of signs of the lie we've been telling about what a string actually is. Because it seems that you can't just compare two strings for equality. And it seems that you can't just copy a string into another just by using the same techniques we've used for chars and for ints and for all of the primitives, so to speak. All of the lowercase types like double and float and char and int that come with C, but string itself is not something that comes with C. So what's actually going on underneath the hood? Well, at the risk of, or in an attempt to be dramatic, today is when we sort of get to take off these training wheels that you might have had in your bicycle for some amount of time, and now reveal that a string is actually a little something more arcane. And you might have seen a glimpse of this maybe in textbooks or Google or online or whatnot, but a string is actually just a synonym that CS50's staff created for a little more complicated expression called char star. Now, char is familiar, character. And for now, you can think of the char as maybe implying that there's going to be multiple characters involved. Because at the end of the day, that's still what a string is. A string at the end of the day is still a sequence of characters. But more precise than that is the question that we're going to explore now. So let me go ahead and do this. Let me go ahead now and take away the layer that is string and look at this instead just in the context now of using char star instead of that same keyword. I'm going to go ahead and create one more file here. I'm going to call it compare1.c, so hopefully an improvement on my previous version. I'm going to go ahead and include cs50.h so I can still use getString and any other functions. I'm going to go ahead and include standard IO so I can actually print things. And I'm going to go ahead and preemptively include string.h so I have some other fancy features available to me. So let's do this now. Int main void, so no command line arguments still. Instead of string s, I'm just going to take off that training wheel. Char star s equals getString, quote unquote s. And then, you know what, let's do char star t equals getString t colon, like that. So the only difference thus far is that I have literally sort of dropped from my vocabulary the word string, and I'm starting to write it as char star instead. It's not multiplication, so there's a limited number of keys on the keyboard, so humans years ago decided to use different symbols for multiple things sometimes, and so that's where we're at. And now recall that last time, if s equals t, I wanted to print out, quote unquote, same, else I wanted to print out different. So I think this is the exact same program at this moment in the story, except I've just changed string to char star. So maybe that's it. Let's see if maybe all I need to do is sort of take away those training wheels, run make compare 1, seems to compile, and then let me zoom in at the bottom here, do dot compare 1, and let's go ahead here and compare again Stelios's name against Stelios's name. Still different. Let's try my name, David. Still different. Maybe it's a capitalization thing. Let's do David. All right, so it's still broken. So obviously, just taking off the training wheels doesn't make the problem better, apparently. We need to actually understand how the bicycle works, if I can really milk the metaphor today. So how does a string really work underneath the hood? Well, you know what? I'm not quite sure how to explain it yet, but I know that I can actually solve this problem by not using equals equals. I can instead do this. If stir compare of s comma t equals 0 of all things, now print that they're the same. You would never know this unless you were told or found it in a reference book or online resource or whatnot that stir compare exists. As its name kind of suggests, it's just succinctly written, stir compare, CMP. So you're comparing two strings, s and t. And if we read the documentation, like the man page or CS50 reference online or Google or whatnot, we would see that the definition of stir compare is this. If s and t are visually the same string, then return 0. Just because a human decided that. If s comes before t alphabetically, return a negative number. If s comes after t alphabetically, return a positive number. So that's kind of nice, because there's three scenarios when you're comparing two things. Either they're the same, or one is bigger, or alphabetically before, or alphabetically after, or smaller. So there's kind of three cases to consider, and we've seen that before when we've written out pseudocode, when testing for things like equality or looking for Mike Smith. So stir compare leverages that same idea. It's just a little messy that we have to use numbers, like 0 for equal, and negative for less than, and positive for greater than. But let me try recompiling this now. Make compare1, and then let me do /compare1, stelios, enter, and now they're the same. Let's try this again. Let's do stelios again, Maria. They're different. So again, proof by example shouldn't be sufficiently compelling, but it's better, it seems. And indeed, it is correct now. So what is it that's going on? And maybe we just got lucky here too. Let me go ahead and iterate on this and just improve things in a couple of ways. Let me go ahead and open up or point out this. Let me go ahead and open up copy1, which is an improvement on our original copy version as follows. Let me do this here. So what's actually going on? So it turns out, actually, let's do this before we jump ahead to compare1. Let's consider what's actually happening in this computer program. So to recap, we're getting a string, calling it s. We're getting another string, we're calling it t. And then previously, we were just comparing equal, equal. But now stir compare seems to solve this problem. So someone solved this problem for us. Let's see if we can't infer what's going on. Well, let me go ahead and just pull up a little chalkboard here of sorts and propose to consider what exactly getString is doing. All this time, we say that getString gets a string from the user and just returns it to you. And indeed, when we did an example the other day and our volunteer was wearing the getString name tag, he just handed me back a slip of paper that said the audience member's name. So getString does work like that, but we only have access to this canvas of memory. So what does it really mean to return a string and to put it somewhere in memory? Well, it turns out when you do a line like this, string s equals get underscore string, there's two parts to this, the left and the right. So what's actually going on? Well, the left-hand side of this expression, string s, is telling the computer, hey, computer, give me a chunk of memory, and I'm going to draw it as a box, and call it s. The right-hand side of this expression obviously does get someone's name, and I'm going to draw that just for the moment as like Stelios' example. So Stelios' name, and just to be super precise, there's a \0 in there, recall. Let's continue that assumption. But what exactly is going in here? Like Stelios' name literally visually cannot fit in that tiny little box. So what is it when Stelios' name is handed to me, I'm actually storing in this little box? Well, what is Stelios' name here actually implemented as? I've just written it out. But what is it more technically, using some CS jargon? It's an array of characters. So let's see that. So let's just kind of draw out what we know is underneath the hood, even though we can just kind of take for granted that this works. So this is not to scale. But each of these characters, letters in his name, take up a byte. They're an ASCII character, so to speak. So I don't know where these things are in memory, but I'm just kind of going to guess. Like, I've been using my computer for a while, so maybe this is at like byte 100. This is byte 101. This is byte 102, and so forth. So those bytes are numbered, whatever the numbers actually are. So given that, the fact that a string is just a sequence of characters, and those characters each take up like a byte of actual memory in your computer, and those bytes can be thought of as having numbers from 0 to like 1 billion or 2 billion, what would you propose just intuitively we put in the box when we get back a string? 106? OK, why 106? If we say 106. So that would be like one. Oh, sorry. Do you mean one? That's my way of writing 100. Do you mean 106 as in 1, 2, 3, 4, 5, 6? This one? No. Oh, just my messily written 100. So you can store the location of where it starts. Correct. So if we fix my horrible handwriting, we could put in this box just the address of that string. That's not his whole name. It's just like the location in my computer's memory of the first character in his name, which feels a little reckless because Stelios' name is not S. But why is this sufficient information to store Stelios' string in this variable effectively? Exactly, the \0 is there. And even though a computer, if you go back to our locker metaphor, kind of has to open each door in order to see what character is behind it, we can do that with just a simple for loop or a while loop. And a computer, given the address of Stelios' name's first character, it's kind of like a map, like X marks the spot. Like the computer can go to that location in memory and say, oh, here is the first letter in his name. And then the computer, if printing out his name using printf or something like that, the computer can just print out the S, then open the locker door next to it. And if it's not a \0, print out the T. Open the next door. If it's not a \0, print out the E, and repeat and repeat and repeat. And as soon as it does get to that special sentinel value, as we say \0, it closes the locker door and stops printing. So because all this time we have been terminating our strings with \0 as a special demarcation, all we need to know logically to store a string is where does that string begin. The upside of which is now we can store just a single tiny chunk of memory. It tends to be 4 bytes or 8 bytes, depending on what kind of computer you have, 32 bits or 64 bits. But what you don't need is as many bytes as there are characters in his name, because those are already using other bytes in memory. So when I now declare T in my first version of the program, string T gets underscore string, quote unquote, T colon, just as my user's prompt, close quote, semicolon. What's happening in this scenario? Well, the logic is exactly the same. This is saying, hey, computer, give me a chunk of memory, call this chunk T, and then even if the human types in literally the same thing, like STELIOS, that is underneath the hood, just an array that we can keep drawing like this. And of course, the computer for us is going to put that \0 because the computer's been doing that for the past few weeks. It's not going to be the same location, though. Maybe this is now at like location 300, and this is 301, and this is 302, and so forth, because the computer's doing other things. It's using memory over here or over here. So it's not going to be in the same location. But what therefore gets stored in T when we assign the return value of getString to T? 300 in this case, and that goes here. And so if we go back to our original computer program, which again was this program compare0.c, why now does it make perfect sense, eventually, that S and T are always different no matter what you type in? Because what's actually getting compared on this highlighted line here when you do if S equals T? The memory locations. You're literally doing the same thing for the past few weeks. You are literally just comparing two variables, S and T. The difference is that now that you've broken the abstraction layer, taken the training wheels off, however you want to think of what we're doing here, you are literally doing the same thing, but you're just comparing two addresses, two locations. You are not very fancily comparing every character against every character to determine what we humans think of as equal or identical strings. So this notion of an address, this notion of a location, is given the buzzword pointer. And a pointer is just an address of something in memory. And you can think of it like literally as like pointing to something. Like what is 100 pointing at? You can kind of visualize it as well. It's kind of pointing to the first byte of some array of memory. And T, meanwhile, you can think of as pointing to, with an arrow, the first byte of some other chunk of memory. And as such, you know what? At the end of the day, we really aren't going to have to care where things are in memory. These are uninteresting implementation details and shouldn't really matter to us because we can talk about things symbolically. We can say S instead of hard-coding the stupid number 100. We can say T instead of 300 and let the computer and the compiler do all that kind of math for us, just knowing we have this canvas of memory at our disposal. And so why does string not exist? Well, this notion of a string, apologies again for my handwriting, is again just a synonym for char star. And this string too is just a synonym for char star. And what does that actually mean? Star is just the symbol that humans years ago decided would represent an address, a pointer, a location. Char is relevant because what type of pointer is this? It is a pointer to what data type? A character, or it's the address of a character. So you can think of it as pointer to, address of, however makes sense in your mind. And so even though this is a string, well, T and S are not pointing at a string per se. If you really like zoom in, they're technically only pointing at a character. And it's our choice of implementation that, yes, we can eventually find the end of a sequence by looking for \0. But this is what's really powerful and also confusing about C sometimes, is that at the end of the day, it's very simple operations. And when you copy something, you're literally just moving one number or one character from one place to another. And if you want higher level constructs like strings, you have to implement them underneath the hood. And this is not sort of a fun way to start programming in like the very first week of a class. Be like, hey, everyone, today we're going to talk about pointers and addresses. Like, it's mind-numbing, it's confusing, and it really doesn't allow us to focus on the algorithms and the actual problem solving. But now we're at the point in CS50 and soon with other problem sets where you want to, or will have problems that really can't or shouldn't be solved by just like numbers and characters and arrays alone. We actually want to leverage the power of our Intel inside and do something more sophisticated. And so we do, at this point, need to understand what's really going on. And that's going to unlock a lot of capabilities. So with that said, if compare 0 was wrong, but compare 1 was right, what can we infer about how stir compare works? Someone wrote this years ago, decades ago even, but what did he or she do in order to implement stir compare correctly, do you think? They gave the same memory location. Can't be that, because they don't have control over the strings I'm comparing, right? I am passing in S, and I am passing in T, and I got those from wherever I want. So 20, 30, 40 years ago, someone only could take in as inputs 2 strings, or technically 2 pointers, or really technically 2 addresses. So what did this person do to implement getString? How about here? Yeah, just intuitively, if this program's correct, stir compare must be doing what we humans thought equals equals would do or might do. And so what stir compare is presumably doing is it's taking 2 addresses, we'll call them S and T, and it's going to those addresses, and it's checking, are these 2 letters literally the same? And if so, it moves on to the next. Are these 2 letters literally the same? If so, it moves on. And the moment it notices a mismatch, what does stir compare probably do? Well, stir compare doesn't print out different. That was me in 2017. Exactly. It would return negative or positive based on whether the string is determined to be alphabetically before or after. And so only if we get to the very end and we see, ooh, we made it to 2 \0s at the same moment in time, can stir compare just return 0 and say these 2 strings are in fact equal. So we too could implement that, right? It just sounds like a for loop, a while loop, just comparing those characters. Yeah? Oh, good. So say that once more. Stemios, OK. OK, so good question. So let's actually see this. Let me make one quick tweak here. And let me go ahead and do this. I'm going to go ahead and do int answer gets stir compare s comma t, just so I can tuck it away in a variable. And that means I can now just do if answer equals 0. So now sorry, I'm the only one who is playing along. So what I just did was this. Let me rewind in time. So just a moment ago, my code looked like this. I was just calling stir compare, passing in s and t, and checking the return value. I'm just going to give myself a variable here and store the return value of stir compare now. And then I'm just going to change this to be answer so that my code is identically functionally the same. It's just now I have access to answer because I want to answer your question empirically. I want to just try this out. I don't want to have to wrestle with the documentation even. Let's just try and see. So let me go ahead here and do this. Print out %i \n. And then even if they're different, let's go ahead. Actually, you know what? I don't even need to put that there. Let's just put it out here. So printf answer is %i, semicolon. Yes. Exactly. There. Precisely my point. So now let me go and do make compare 1 / compare 1. And let me zoom in here. And let's type in Stelios and his evil brother Stemios. Enter. And so the answer is -1. Why? Well, alphabetically, Stelios with the L comes before Stemios with an M. And so we get back a negative number, which happens to be -1. But I think the documentation just says it's a negative number. So you don't check for -1 per se. And now if we reverse them, let's just do a little quick check here. If now we do the evil brother first and then Stelios, enter, now it's a positive value because I've switched the order. And of course, hopefully, all this time, when you type in Stelios both times, the answer is in fact 0. So a very simple idea. We're just getting back an integer, but doing something ultimately pretty powerful with it. So what about copy? So copy needs a better solution than we have at hand. Because when I do copy, for instance, let me go ahead and just clear this and propose what's actually going on. So with copy, I have string s gets getString. But let me drop the training wheels again. So let me just write it as what it really is. Char star s equals get underscore string, and then the prompt for the user was quote unquote s. And now that gives me a picture in memory like this called s, and that's going to give me a string which is going to look like this. And let's go ahead and do Stelios' name again. So Stelios with a really big \0, and my array as before. And you know, I don't care about the addresses anymore. This is like an uninteresting story to keep making up numbers. Let's just point at it conceptually. So picture is worth as many words. But now in my second program, remember copy 0. Let me just pull it up to remind. In copy 0, recall, we had this code where I copied a string's address by claiming just t gets s, t equals s. So what's the implication now for this? Well, let's just do char star t gets s. And again, the only thing I've changed now is I've changed the word string to char star, just to be more pedantic about what's going on. This gives me what kind of picture? Well, it gives me a little chunk of memory called t. But to be clear, what goes in s? Just an address, right? Char star makes super clear now that t is an address. So all we can fit is an address here. We can't fit like STELIOS and so forth. We can only fit an address. So what address? Well, let's go back to the previous story. If we did have numbers like 100 and 101 and 102, as such, technically in this box S is just the number 100. But again, who cares? Like we can just draw pictures at this point. What is in t? The same thing. So it's also 100. But again, who cares about the numbers? It's kind of conceptually the same thing. So at this point in the story, when I have written string t gets s, it is working correctly. It is copying what's in s and putting it in t. But what's in s is an address. And so that's therefore the same thing that's going to be in t. Yeah? So how is the upper function able to work? But work in what sense? Because recall that when we used copy 0 before, let me zoom in here, /copy 0, and I typed in my own name, all in lowercase, it worked in the sense that it seems to have changed both s and t. So it kind of worked, but it overworked, if you will, because it should have only changed the copy. So why is that? Well, again, let's go back to kind of the fundamentals here. If the copy 0, and let me go into highlight these lines to which I've added some comments now. These are the lines of code to which you're referring. T bracket 0 gets to upper of T bracket 0. So I kind of read that now, even though it's a little cryptic, as pass the first character of T, T bracket 0, into the to upper function. And if it's a little d, become big D. If it's a little a, become big A, and so forth. And put that back in the same location. But the catch is that, OK, so let's do that on the screen. So T bracket 0 means go to the first element in the array. And it happened to be a little d in the example I did, and capitalize that letter. Here it would be s, but it's already capital. So now I'm kind of combining the stories. And so when you change the first letter of t, you're literally changing the first letter of s, because t and s are both kind of like maps, little treasure maps that lead to literally the same location. And so here, too, is something that I've not yet stated clearly. Even though t we've been calling a string, and now we're all of a sudden calling it a char star, you can still manipulate its characters using square bracket notation. So when you see something like t bracket 0, we've all known for the past week or two, and especially with Caesar and Vigenère, that that just means change the 0th character of the string called t. But a little more technically now, if t is a pointer, it really means go to the address and then get bracket 0. So there's a little more work that's been happening. It's just more of a mouthful than we needed a week or two ago. So what is the solution then to this fundamental problem? Copy 0 is still broken. You might understand how it works, and if not, you certainly read through this again, or take it a little slower, or use the debugger to see what's going on. But for now, it's broken. So what's the fundamental conceptual solution here? Yeah, set up two, and not just two addresses, a little more. To what? OK, sure, two houses, right? One for Stelios and one for evil twin or whatnot. The key being, we need two of these chunks of memory to be different strings. We don't just want two addresses. So we need to kind of fill in this gap here. So like, how do I get an extra chunk of memory so that I can put a copy of S and a copy of T and a copy of E, L, I, O, S, /0. Like, what mechanism allows me to get as many characters as I need to fit the original name so that I truly have two copies so that this picture is not this anymore? How do I create a scenario in a correct version of my copy program so that T actually points to a true copy, so that, to your point, when I change the 0th character, I'm changing the 0th character of the copy, not of the original? Well, we don't have this answer just yet. But we do if we introduce this one function here. So I'm going to go ahead and open up here proactively copy1.c, which I wrote in advance, which looks the same up here, except for at least one. You'll see eventually. Okay. So I'm going to open up this program I wrote in advance called copy1.c. And it's almost the same, but I've added a few more lines of code. So here's a familiar line now. Last week it was string s gets getString. Today it's char star s gets getString, because we now kind of know what's going on underneath the hood. And just propose. Now I'm just being a little anal here by writing more lines of code, line 12, 13, 14, 15. Why do you think I might be having this if condition all of a sudden today? This is technically better, and I've kind of been cutting some corners the past couple of weeks. Yeah, it's that essentially is that, just to make sure that S is actually a string. Because it turns out my computer, as you know, has a finite amount of memory, right? I only have so many of those little black chips. I only have so many bytes or gigabytes in my computer. And even though we're really not taxing my computer's capabilities with typing Stelios' name or mine, theoretically, my computer could run out of memory. And frankly, if your Mac or PC is ever like frozen or crashed or hung or whatever, maybe it ran out of memory, it just didn't handle it well, and so bad things happen. So bad things can happen. So how do we know if something bad has happened? Well, it turns out that getString, if you read the documentation for it, and you might have or might be for the current problem set where we ask you to consider what it's really doing, it turns out that getString can sometimes have problems out of memory. Damn it, like what do you do? If the user typed in like his or her whole like life history and it couldn't fit in memory, what do you return? You don't just return part of their life history, just a few of the words or paragraphs. You instead return a special value that we've not used until now. And that special value is a keyword that can actually be something called null, which is confusingly named because NUL is the name that humans gave to \0. NULL is the word people gave to this notion today. So getString can, in some cases, fail because you run out of memory. The user typed in too many characters at his or her keyboard. So getString can return null. If you don't check for null, maybe your program will crash or hang or do something unpredictable. And so to hedge against that, we ask this. And this is a very succinct way of doing this. Let me actually be a little more verbose. If s equals null, return 1. So there's a couple things going on here. Line 12, if you believe me that getString can sometimes return a special value, literally NULL, all caps, no quotes, it stands to reason you can check for that and do something based on that decision. And that decision can be to return 1 or 2 or -1. So long story short, main, recall that main, we've typed it a couple of ways, sometimes with command line arguments, sometimes with not, without. But the word int has always been there now for weeks, and I kind of like just ignored it for the past several weeks. It turns out that main is a little special, and humans years ago decided that main will just always return an int. And that integer is used by the computer, like Linux or Mac OS or Windows, to just know if a program succeeded or failed. If a program worked OK, succeeded, main is supposed to just return 0. If something goes wrong, main is instead supposed to return 1 or 2 or -1 or -2, any number of values except 0. 0 is the only number in the world that means OK, which is a little paradoxical because it usually means false or off. But there's 1 0, and there's like an infinite number of other numbers, which in a lot of things can go wrong in programs, is the thinking there. So in fact, if you've ever on your Mac or PC seen an error message that's like error -239, like what the hell is that? It just means that some program returned a number that some human decided would represent whatever problem just happened. I, thankfully, don't have a very big program. Not that much can go wrong. So I'm just returning the first number I thought of, which was +1. But it's kind of arbitrary. But at least it's not 0. So now I'm doing a little check there. But you know what? It turns out null is just a synonym for 0, it turns out. More on that before long. So what does the exclamation point mean in C? It means not. Like, reverse the answer. So this is like saying if not S. So if S is null, according to my definition today, it's equal to 0. So if not 0 means if true, then return 1. And this is like completely backwards and confusing, I think. But this is a way of saying, long story short, if something went wrong, return 1 now. That's all. That's all. So let's not dwell too much on that, because that is not the juicy part. The juicy part is this scary thing. So let's just consider for a moment what's going on. This is probably the scariest line or longest line of code we've yet seen, but it's doing something relatively simple. What's going on here? Well, on the left-hand side, let's pluck off the easy one. Someone in English, just tell me, what's the left-hand side doing to the left of the equal sign? Sorry, say again? Declaring a string. Give me a string called s. But let's be a little more precise. Give me a variable called s that's going to store today not an array, but a pointer, or the address of a character. So again, if we really want to be like uptight today, yes, it's declaring a string called t. Yes, it's declaring a string called t, but more precisely, it's declaring a variable called t that's going to store the address of a character. So it's more words. This is why code is nice and succinct. You can say in a few characters what just took me a whole sentence. So that's all that's happening on the left-hand side. So again, if we draw this as a picture, what's happening now is that char star t just gives me this tiny little box. That is not nearly enough room to store Stelios or David or any number of other names. So the magic must be in the right-hand side of this expression. And this is a bit of a mouthful at the moment, so let me distill it to its essence. It turns out there is a function in the world called Malloc for memory allocation, succinctly named. It takes one argument, the number of bytes you want. And Windows or Mac OS or Linux, whatever your computer is running, its purpose in life is to hand you back a chunk of memory that is equal to that length, 5 in this arbitrary case. So what does that mean pictorially? If I call malloc 5, that means that the computer finds somewhere among all of those green circuit boards and those black chips we've been talking about, it finds me a chunk of 5 identical bytes that are back-to-back-to-back, identically sized bytes that are back-to-back-to-back-to-back, and then returns to me, malloc does, what do you think? The address of? Exactly, of the new place you've just allocated memory. So if this is arbitrarily at location 400 now, and 401, and so forth, what malloc returns is just a number, more precisely an address. It returns the address of the beginning of that chunk of memory. But it's worth noting, malloc is completely generic. It just gives you a chunk of memory. It has nothing to do with strings or integers or anything like that. So the burden is entirely on you to know how many bytes you asked for. So I literally hard-coded 5, so hopefully I, the human, remember that when I write more lines of code. But notice absent from my picture is what, deliberately? There's no \0. This isn't necessarily a string. Maybe this is a really long number or something else, a data structure as we'll soon call them. I just have to remember how long it actually is. And in particular, it's worth noting now, and we've used this terminology before, when you don't initialize memory yourself, you should think of those values in almost all contexts as just having garbage values. Maybe it's the number 1, maybe it's a 0, maybe it's the number 42, anything. It's just garbage from that memory maybe having been used previously in your program for some other purpose before you didn't need it anymore. So now if I go back to my code, 5 doesn't quite work because it doesn't even fit my name. D-A-V-I-D is 5, but how many bytes do I need to store my own name? 6 because of the \0. So if I want enough memory to store my name, I actually need this to be 6. But this is obviously kind of stupid because now I can never support, I can't even support Stelios. I can support me and Maria and some other short names, but not longer names. So that's why at first glance the code was scarier. But let's just break it down. This expression here in parentheses is asking probably a familiar question. What is the length of s, the string the human typed in, and then why the +1 to be clear? The \0, right? Strlang gives you the human length of a string, like what we view on the screen. That +1 gives us the \0. And then just to be super precise, I want that many chunks of memory times the size of the chunk of memory that I want. And technically in C, a char is always 1 byte. So technically this is not necessary in this context. But just to be super clear, I decided to be super pedantic and just say, give me this many chunks of memory, each of which should be this size. And it turns out in C, there's an operator called sizeOf, where you just specify what type do you want to get the size of, and it will just tell you 1, 2, 4, 8, whatever it is. So now, even though this looks pretty darn cryptic, all it's implementing is this picture, and it's storing in this variable t the number 400. Or if, again, your sort of eyes glaze over at that level of detail, just think of it as an arrow pointing at the chunk of memory. So when I then do this, just intuitively, why am I asking this question, if not t? And again, if not t is the same thing as saying if t equals null. Why am I doing this? You've just met Malloc, but maybe what could go wrong? Garbage values are OK. I can deal with those because I can just change them. Say again? You don't have enough. Maybe I said, give me Malloc of like not 5, but give me Malloc of like 5, 0, 0, 0, 0, 0, 0, 0, 0, 0, like 5 billion. Billion. Maybe I said, give me 5 billion bytes. And the computer just doesn't have it. So it's not going to return me part of the memory I want. It's just going to say, like null is the return value. It failed completely. So that's why we check for it, but that's all. It's just another form of error checking. And then now, notice the kind of work I have to do. If I want to copy the string, it's clearly today not sufficient to just do the equal sign, moving from right to left. You have to do the work yourself. So here's a for loop that we might have used a week or two ago for just iterating over strings. And that's all I'm doing. I'm iterating over s and copying each of s's characters into t by just this line of code here. And now why, this looks like a bug in almost every other context, why am I starting at 0, iterating up to the length of s, but technically up through the length of s, even though I'm 0 indexed? Right? Like in almost every for loop we've written in the past, we've done this with strings. Why did I deliberately add the equal sign today? Yeah, you wanted to include the null character, and ul, just one L, the special \0. Otherwise, you might end up putting like D-A-V-I-D garbage value, which might then be printed on the screen. It might be considered part of my name. And so there could be any number of garbage values, all of which will be conflated for letters of my name. And so now when we do this line of code, which we did have before, we are literally only capitalizing the first character of t. It is completely independent of s, because the picture we've done is have not just this, but an identical chunk of memory that has those same characters down there. And we're only mutating or changing those characters. So when we finally print the result down here, s and t, we're printing the original s and the copy of s with its first letter capitalized. And that is why then, when I did /copy1, whoops, in my source directory, so if I go into source 4, and then I do /copy1, damn it, make copy1, and I do /copy1, and I type in David all lowercase, I capitalize only t, and if I run it again, say with Stelios, all lowercase, I capitalize only t, because now I'm actually manipulating the memory as I originally intended. Any questions there? OK, that's a lot. Let's take a 5-minute break, and we'll come back with one more layer. All right. So we're back. And to recap where we're at, we sort of revealed what a string actually is. It's just a char star. Star means it's an address or pointer location, however you want to think of it. And the type in front of the star means what is the address of. And we've been talking char star, so that means the address of a character, which we can think of higher level as just a string. So if you're comfortable with that, and even if you're not, it'll sink in over time. But if you're comfortable with at least the claim that a string is just the address of a single character, then let's consider what we've been doing all this time by way of this example. String 0, which is on the course's website if you'd like to look later too. And notice I'm just following a familiar paradigm now. I'm just getting a string, and I'm storing it in S, which is technically a lie. I'm storing the address of the first character of that string in S, to be super precise. Then I'm just making sure, so long as if there was not enough memory for this, return 1 and just abort the program. If there was plenty of memory, do this for loop. And we've done this for the past couple of weeks in various contexts. Initialize I to 0, initialize n to the length of that string, and then go from I less than n just to print out each character at a time. And just to be clear, because the \n, if I type in like stelios, it's going to print S-T-E-L and so forth, each character on one line. So this is sort of week 1, week 2 stuff at this point. But today, just realize there's an equivalence to a fancier syntax, but maybe just less intuitive. If I open up string 1 now, notice I again do the same thing. Just get a string, call it S, make sure there's enough memory, and then move on. And what do I do here? So this is kind of funky. So it's still the same for loop from I to n, but I threw away my square bracket notation, which we've been comfy with perhaps for the past few weeks with strings. And square brackets allow me to index into an array, and an array is just a chunk of memory. But you know what? Those have really just been what a programmer would call syntactic sugar, which is a really weird way of saying they're like a feature of the language that just kind of simplify aesthetically a fundamental idea. And today's fundamental idea is that characters have addresses, and therefore a string is just the address of a character, or the first character of a string. And so what could this possibly mean? This is an example of a fancier technique called pointer arithmetic, which, no surprise, involves pointers and arithmetic, adding them together. But what am I doing? Well, just to be clear, in this example, what is S on line 19? Good. It's the address of the string that the user typed in. So if it's stelios, it's the address of capital S, or if it's David, capital D, or whatever the character is. S is the address of the string, or more precisely, the address of the first character in the string. I is what in general? It's just an integer. It starts at 0 because of my for loop, and it goes on up to the length of the string. So it's 0, then 1, then 2, then 3. And what do we know about strings? Strings are sequences of characters back to back to back. And every character is 1 byte. So beautifully, if you think about what's going on underneath the hood, if this is location 400, I don't even need to write the other numbers. You intuitively know that this is location 401, 402, 403, 404. It's just arithmetic to get from one to the other. And so it stands to reason that if you know that, you can kind of throw away the training wheels or the syntactic sugar of square brackets even, and just say, you know what? I want to print out the character that's at location S plus some offset, so to speak, plus 0 more bytes, or 1 byte away, or 2 bytes away. So I just do S plus I. S is the address. I is a number from 0 on up. So it just kind of moves the address from left to right. But there's one funky syntax, and this is by far one of the most annoying design decisions in C, especially when you're first learning this stuff. There's another damn star here. And the star means something different based on the context. So notice, previously, when we used this star, well, previously, star meant multiplication, and life was much simpler. Today, star means it's an address of something. But there's 2 different contexts in which a star is going to appear moving forward. Here is where we're declaring a variable. So anytime you see a star that's clearly not being used for multiplication, and instead is something fancier, like this, if there's a data type to the left of the star, that means you are declaring a variable. Specifically, a pointer variable that points to that type of data type, like on the address of a character. If, though, in another context, you see the star used in a weird way, like it's not multiplication because like there's nothing to the left of that star. So it's not like grade school math here. It's just a star, and it seems to be kind of related to the parenthetical expression that follows, s plus I. So s is an address, I is a number, s plus I is therefore just a different address. So the star operator in this context just tells the computer, go to that address. Follow the treasure map and go to where x marks the spot, where x is just s plus I in this case, the address. So when you see the star, when it's not multiplication and there's no data type to the left, it means don't give me a pointer, go to that pointer, go to that address. And so this for loop now is equivalent to the program we saw just a moment ago, even though it's kind of crazy looking. Which one is better? I mean, honestly, when I write code, I still generally write it this way. The syntactic sugar is nice. It's just a little easier to read. I don't have to do arithmetic in my head. And frankly, it sort of just reads more intuitively than this version. But both are correct. And among today's goals are to reveal why this other fancier version is also correct. Let me introduce one other example that kind of takes things in the opposite direction. So all this time, we've had these training wheels of getInt and getString. And frankly, that's just because in C, it's really annoying to get input from the user. Like, C does not make it easy, especially if you want to add error checking, right? If you guys have used getInt or getString, if you use getInt and you don't type a number, you type like a word, it's going to reprompt you and reprompt you and reprompt you. So there's a lot of like those features that are just nice in the first few weeks of an intro CS class when it's hard enough to get the parentheses and the semicolons right. It'd be nice if at least when you ask for an int, you get an int back. And that's why we have those training wheels. But if we take those off and take away even today, we're not going to yank it away, but if you sort of decide to let go of the CS50 library, we have to come up with other ways of getting user input. So let's use today's ideas to do exactly that. It's a super small program. It's a little cryptic looking, but let's see how you can get an int from the user without using getInt. Here is one way. Hey, computer, give me a variable called x in which to store an int. So that's like week 1 stuff. Just give me a variable. No magic. This is also week 1. Like just print out x, and then down here, print out a prompt for x, and then down here, just print out whatever is in x. So the only new line is this one here, scanf. Scan means to kind of read from the keyboard, like scan whatever the user typed in. F means formatted, and that means you can read a certain type of input from the user. So %I, recall, has generally meant integer. So scanf borrows some of the syntax of printf, but it's kind of the opposite direction. Printf goes out to the screen. Scanf comes in from the keyboard. But dang it, if there isn't this one new piece of syntax. But you can maybe reason through what's going on here. So x is an integer, but we want to store something in it. And up until now, anytime we wanted to store something in an integer or whatever variable, we just use the assignment operator from right to left. And that's exactly how getInt works. But getInt underneath the hood uses other techniques that we haven't yet seen. And what it could be implemented as, though it's actually even fancier than this, it could be implemented using scanf. The way scanf works is this. Scanf takes in a format string like this, which just tells the function what type of data to expect. And then you pass in not a variable, but the address of a variable. So the ampersand means get the address of some variable. Why is this useful? Well, when you just do int x, like here, like we've done for weeks, you just get a chunk of memory. Ampersand x figures out in memory where that is, and maybe it's at address 500, and so ampersand x literally returns 500. So scanf then, as input, takes this format string, which just tells it what kind of data to read, and then it takes the address of a variable, because scanf's purpose in life is going to be to go to that address and put at it whatever number the user typed in. Now, why is this necessary? Why in the world can I not just do scanf x? Well, it's related to a problem we ran into earlier. Recall that when Kate came up and did the swapping of those two variables, we claimed that logically she was correct, and we claimed, or I claimed, that my code was similarly correct, or at least a decent translation of what she did here in reality. But this did not work. It still left 1 in x and 2 in y and never actually changed them. Well, why is that actually the case? Well, let me go into NoSwap in the IDE. Let's go ahead and do this. Let me go ahead and use my old friend eprintf and say a is %I, and then enter a there. And then here I'm going to go ahead and say b Actually, let me do it in one line just to kind of simplify the code. So A is %i, and B is %i. And I'm going to pass in A and B here. I just want to see inside of swap if Kate's logic is actually correct. And maybe A and B are being swapped, but maybe somehow X and Y are not. So let's actually see what's going on here. So if I go ahead now and run make no swap to compile it. Oh, and I got to include CS50's library. Include CS50.h. Let me go ahead and compile this. Make no swap. / no swap. Let's see what actually happens. So x is 1, y is 2, and at the end of the story, x is 1, y is 2. That was the problem. Now I'm digging in a little deeper, and I'm looking inside of no swap. So at no swap line 20, I printed out a is 1, b is 2. Oh my god, like Kate was right. Like her code works, but it doesn't work lastingly. Like it works within the function, but it seems to have no effect on passing in x and y. So it's kind of like she swapped it on stage, but as soon as she stepped off stage, they were kind of back the way they once were, which is just weird. So what's actually happening? Well, it turns out that when we talk about a computer's memory, we have this layout here. And there's different areas of memory, and the two we're focusing on today are just these, stack and heap. And all this time, when we've used Malloc to get more memory, that memory has been coming from the so-called heap, which you can think of as like the top of your memory right now. Though technically you can think of it as the bottom, but it's from a specific area of your computer's memory. The stack, though, is used differently. The stack is a region of memory that any time you call a function, the memory for your local variables comes from the stack. And you get a sliver of memory from the so-called stack, just like you would like get a tray off of a stack in a cafeteria or dining hall. So what does this mean in code? Well, if we look at the code for no swap, and we see here the code as follows, that main declares x and y and takes no command line arguments, but swap takes in 2 arguments, a and b, and has one other variable called temp. Where is that memory actually going? Well, you can think of your computer's memory again as having these 2 regions, heap and stack. And previously, Malloc was taking memory from up here. Now let's focus on the bottom of this region of memory, which we can think of as this here, stack. So this is like where all the trays go in the cafeteria. And it turns out when you run a program like no swap, this region of memory at the very bottom is where any of main's local variables go. And to be clear, what local variables does main have? What are they called? Just x and y. So that means somewhere in this sliver of memory, there's space for something called x, and there's space for something called y. And I, the programmer, put the numbers 1 and 2 there. So that's what my computer's memory looks like in this program. But when swap is called, much like I called Kate up onto the stage, she technically gets her own memory space for any work she's actually doing. And so swap gets its own slice, or technically frame of memory, tray of memory in some sense. And in there go any of hers or our swap function's local variables, which are called what again? A and B. So A and B and one more? Temp, a third one. So swap, in its stack frame, more precisely, has room for 3 local variables, A and B and temp. So what, though, happens when main calls swap? Anytime you pass a value, an input to a function, that receiving function gets a copy of the value. So as soon as you call swap, x gets copied into A, y gets copied into B, and then when Kate finally used the empty cup, or swap uses the temporary value, some other value gets copied into temp, like 1, in order to keep that value of A around. So when Kate then swapped the Gatorades, and when swap does its thing equivalently in code, it does actually work. 1 becomes 2, and 2 becomes 1. But as soon as swap returns, what happens to that memory, perhaps? It just gets thrown away. Like the stack, as the name suggests, is constantly growing, but then it's constantly shrinking as soon as these functions return. So as soon as swap is done doing its thing, and as soon as like Kate walks off the stage, it's as though she was never here to mutate or change x and y, because all the work she did is just kind of ignored thereafter. And that's because functions don't have access to each other's memory spaces. They are only getting copies of what's actually passed in. So what then is the implication, or what is the solution here? Well, let me go ahead and open up swap.c, which, as the name suggests, actually does do a swap. and show how I've changed this. So in main, I still declare x and y as 1 and 2. I changed, though, line 13 to use ampersand, which again means what? Not go to that address, the opposite. Find the address, or get the address of x, get the address of y, and then pass those in to the function. Meanwhile, and frankly, it's understandable if this is kind of visually overwhelming syntactically because of all the damn stars, but what is swap being declared now? It's not taking an int. It's not taking a second int. It's taking the address of an int and calling it a, and it's taking the address of another int and calling it b. Different idea. Then, most confusingly of all, but it'll take time with practice for this to sink in, this is implementing now what we want. This is just storing in a local temporary value whatever the contents of A are, because star, as you said a moment ago, albeit prematurely, means go to the address in A, and that's going to give you the number 1, because 1 is at that address, so put 1 in temp. This means go to the address in A again, and put at it whatever is at the address in B. So take the 2 and put it at whatever A is pointing at. And then the final switcheroo is go to the address in B and store, quite simply, the number 1. So what does that mean for our picture? Because the syntax, frankly, does not make this all that much fun. For our picture here, if we consider what's actually happening underneath the hood now, let me just kind of tidy this up and then go back to a cleaner chunk of memory here. Temp is going to be the same as before. It's going to store just an int. But A and B are fundamentally different. And I don't quite know what to draw there because I need to be a little more precise. So let's go back to our original example where maybe this is byte 100. Maybe this is byte 101, and so forth. So what goes in A, to be clear, in the correct version of swap? It takes the address of an int, which would be like 101. And then it takes the address of an int, 100. And then it takes the address of the other int, which would be 101, which are not the numbers we want to swap, but they're like two treasure maps that lead to the original x and the original y in someone else's frame on the stack. So a function can only change another function's memory if you give it a map to that or those locations. And so now, because of all the crazy uses of star in our code, we're going to the address 100, which means go here, and grabbing its value. We're going to the address in B and getting its value here, moving them around so that these values don't change. But when swap is called in this version, 1 becomes 2, and 2 becomes 1, because swap is a little more sophisticated now, and it's like using these stars to follow a treasure map, go to this address, go to that address, and move those values around. And as complicated, honestly, as this might feel or actually be, realize that it boils down to just these two primitives. Get me the address of something with ampersand, and go to the address of something using star. They kind of undo each other. And just using those two new ingredients, albeit with some strange-looking syntax, can we start to go really anywhere we want in a computer's memory. So if we go back now to scanf, does it perhaps make more sense as to why scanf needs not x, but the address of x? If we just passed in x to scanf, that would be like saying, here is an integer. Do whatever you want with it, because I'm not going to see the difference, just like with the original no swap version. But if I say, here is the address of an integer, scanf can go to that address and put any number it actually wants there. And similarly, let's do this. Scanf1, the world was so simple just a moment ago, but I can break my world very quickly with this example. Here is maybe an incorrect implementation of getString. Recall that getString gets a string from the user and returns the address there too, as of today. But here are 4 lines of code that are kind of just a translation of the integer example to strings. But strings are different, right? This is saying in line 7, give me a pointer to a character. Give me space for the address of a character. This is just saying, hey, printf s:. Scanf %s feels right, because that's what printf would use, and pass in s, and then print out whatever s is. But there's a problem here. S is indeed a pointer already, so I don't need the ampersand. S is an address. That's all scanf expects. But if I say to scanf, Here's the address of a pointer. It happens to be called S on line 7. What is that really? What is at that address? Say again? It's not even that. Because a pointer, char star S, is just the address of a character. But what goes in variables by default in a program? Garbage values. So this is some like random address is in the variable called S. So it is the address, but God knows where that address is in memory. So this is like giving Scanf a map to like some random location, some garbage value, and his purpose in life is to go there, wherever that is, and change the contents by putting whatever characters the human has typed in. So this is like very bad, because what I've not done is build in space for the actual characters in Stelios' name, or Maria's name, or mine. For that, how can we actually get at that? Well, let me open Scanf2, also online, to look at later. And how have I mitigated this, at least in part? Well, in this case, I'm saying, like S is going to be an array of characters, specifically 5 of them. And it turns out, because of the syntactic sugar, really, and technically a more sophisticated feature than that, I can pass in the name of an array to scanf, or any function that expects the address of something. I can pass in the name of an array, and it will be treated as a pointer. And so scanf will now put at that address whatever the human types in. But there's a danger. What could go wrong given that logic? Yeah. Exactly. If you type in something long, something bad is going to happen. When I declare S with char, S bracket 5, close bracket, that means literally give me an array in memory that can hold 5 things that therefore looks like this. S, when passed into scanf, is like saying, OK, there's the address of that chunk of memory. But if we type in like Stelios' name at the keyboard and the programmer has only allocated enough memory for 5 total characters, scanf's not going to know the difference because there's no \0, there's no fanciness. It's not yet a string. It's a chunk of memory. And so O and S and the \n are going to end up in no man's land, memory you did not ask for. Maybe you're tripping over Maria's name or something else altogether, and this is when computers crash. You have an overflow of the buffer or the chunk of memory that you've actually allocated. And we can see this a little more playfully thanks to a friend of ours at Stanford, Nick Parlanti, who spent quite a bit of time, I think, with claymation. And so in just a moment, you're going to see the screen. Nick Parlanti at Stanford put together the following claymation that shows us a little world of Binky and takes a look at some C lines of code and translates them into some claymation fun.
Hey, Binky, wake up. It's time for pointer fun.
What's that? Learn about pointers? Oh, goody!
Well, to get started, I guess we're going to need a couple pointers.
OK, this code allocates 2 pointers which can point to integers.
OK, well, I see the 2 pointers, but they don't seem to be pointing to anything.
That's right. Initially, pointers don't point to anything. The things they point to are called pointees, and setting them up's a separate step.
Oh, right. I knew that. The pointees are separate. So how do you allocate a pointee?
OK, well, this code allocates a new integer pointee, and this part sets x to point to it.
Hey, that looks better. So make it do something.
OK, I'll dereference the pointer x to store the number 42 into its pointee. For this trick, I'll need my magic wand of dereferencing.
Your magic wand of dereferencing? That's great.
This is what the code looks like. I'll just set up the number and...
Hey, look, there it goes. So doing a dereference on x follows the arrow to access its pointee, in this case to store 42 in there. Hey, try using it to store the number 13 through the other pointer, y.
OK, I'll just go over here to y and get the number 13 set up, and then take the wand of dereferencing and just... Whoa!
Oh, hey, that didn't work. Say, Binky, I don't think dereferencing y is a good idea, because, setting up the pointee is a separate step, and I don't think we ever did it.
Good point.
Yeah, we allocated the pointer y, but we never set it to point to a pointee.
Very observant.
Hey, you're looking good there, Binky. Can you fix it so that y points to the same pointee as x?
Sure, I'll use my magic wand of pointer assignment.
Is that going to be a problem like before?
No, this doesn't touch the pointees. It just changes one pointer to point to the same thing as another.
Oh, I see. Now y points to the same place as x. So wait, now y is fixed. It has a pointee. So you can try the wand of dereferencing again to send the 13 over.
Okay, here goes.
Hey, look at that. Now dereferencing works on y. And because the pointers are sharing that one pointee, they both see the 13.
Yeah, sharing, whatever. So are we going to switch places now?
Oh, look, we're out of time. But just remember the 3 pointer rules. Number 1, the basic structure is that you have a pointer, and it points over to a pointee. But the pointer and pointee are separate, and the common error is to set up a pointer, but to forget to give it a pointee. Number 2, pointer dereferencing starts at the pointer and follows its arrow over to access its pointee. As we all know, this only works if there is a pointee, which kind of gets back to rule number 1. Number 3, pointer assignment takes one pointer and changes it to point to the same pointee as another pointer. So after the assignment, the 2 pointers will point to the same pointee. Sometimes that's called sharing. And that's all there is to it, really. Bye-bye now.
So in a moment, we're going to transition to one of our domain-specific problems, namely forensics and the art of recovering information that may have accidentally or deliberately been deleted. But those of you in Elliott House might remember this shot of like the back right corner of the Elliott House dining hall. One of the undergraduate dining halls here. And this is where I was like 20 years ago when I finally got pointers. The key point being it was not in the lecture hall, and it was not like the first time I sat down with the problem set related to pointers, because this topic in particular in CS50, and specifically in this language C, is definitely tough for a lot of people. And if you totally followed everything thus far, that's great. You're already ahead of where I was. But more so than most any other topics in this course, rest assured that if it takes a little while for this to sink in conceptually and for it to kind of come out of your fingers syntactically, that's normal. Or at least if I'm normal, it's normal, because that was precisely my experience. And I mean it. Like, it sunk in literally in this location when my teaching fellow at the time, Nishat Mehta, who was like a year or two older, I think a senior in Elliott House, which is why we were there, he was sort of walking me through it again, maybe the second or the third time. And then finally, that proverbial light bulb went off. And so keep in mind, more so than most any other topic, that here too might be your experience as well. So here, of course, is Zamila, one of our senior-most staff who appears in the course's walkthroughs for various problems. And you'll notice that it seems to be a pretty high-quality photograph or frame from a video. But it seems to be the case that in Hollywood especially, you can always do what's called enhance, which is like the verb that whenever you want to find out like who done some crime, you enhance the image and there he or she is in the glint of someone's eye or contact lens or something like that. So this affords us an opportunity, nicely enough, to kind of continue along a trajectory that we've been on the past few weeks, whereby with problem set 2, we looked at the underlying representation of strings via cryptography and Vigenère and Caesar and so forth. And then this current week, you're focusing on music and the underlying representation of sounds. And this coming week, we focus on the underlying representation of imagery, of which this is, of course, just one example. But it's worth noticing that if Zamila is suspected of something and we decide, or rather, we got to spin it the right way, if Zamila witnessed something and we want to see in the glint of her eye who done it, this is about all you're going to see, because just as in our computers where we have a finite amount of RAM or hardware, so in an image is there a finite amount of information in the zeros and ones that compose the GIF or the PNG or the JPEG or whatever the file format actually is. And indeed, if you zoom up closely enough on this photograph of Zamila, you will see the so-called pixels or dots, because an image is just a bunch of rows and columns of dots, each of which is colored. And I'm hard-pressed to imagine the reflection of any crime being committed based on the glint of someone's eye. And yet, nonetheless, if we could dim the lights for a few seconds, there's such claims in Hollywood as these.
He's lying. About what? I don't know.
So what do we know?
That at 9:15, Ray Santoya was at the ATM.
So the question is, what was he doing at 9:16?
Shooting the 9mm at something. Maybe he saw the sniper.
Or was working with her?
Wait. Go back one.
What do you see?
Bring his face up. Full screen.
His glasses.
There's a reflection.
the Nuevita's baseball team. That's their logo.
And he's talking to whoever's wearing that jacket.
Okay. So, like, that's not happening. Like, this is all that is in the information. And so this is a wonderful opportunity in a pretty cool sounding and actually cool world of digital forensics for us to bridge a couple of our worlds now, right? Up until today, we really only had arrays as our only data structure, the only way we could lay out more than just like individual types of memory. But once we have arrays, that allowed us to start talking about strings, and it turns out strings can be represented really as just addresses, and so that now that we have addresses, we can kind of stitch together any kind of structures we want in memory. Not everything has to be back to back to back. And this means we can now start to think about how we would store information permanently on disk, like on your hard drive of a computer, how you can solve problems more efficiently. And we'll explore that by first considering how you represent even information like this. Well, let's try to take away some of the complexity of Zamaila's photograph here and just boil her down to this happy, smiley face. This is perhaps the simplest image we could create using zeros and ones, because if you think of like white dots as just being represented by ones and black dots as being represented by zeros, or vice versa, it doesn't really matter, you could construct an image from a grid of bits, zeros and ones, if you just interpret them and present them on the screen according to some pattern or rule of thumb like that. And here then is an image. It's got rows, or scan lines as they might be called, and columns that represent the individual dots, or a monitor's interpretation of those zeros and ones. Now, Zamaila, of course, has many more dots than just the couple dozen we saw on the screen before, but it's the exact same idea, because indeed, if we zoom in even on the finest detail of Zamaila's photograph here, do we actually see the actual dots? But instead of just using an individual bit, 1 and 0, because if you've only got 1 bit per pixel or per dot, you can pretty much do no better than 2 colors, black and white, red or blue, whatever 2 colors you want. You got to pick something, and that's when you have very limited colors or black and white. So in Zamaila's case here, it turns out this is like a JPEG, pretty common for photographs and the like. Typically, like as many as 24 bits are used for every dot. And with 24 bits, you can express any number of millions of numbers, which means you can get like light blue, dark blue, hot pink, purple, and any number of colors in between from the rainbow, because you have so much expressiveness with that many bits, way more certainly than zeros and ones. Turns out JPEGs are a little special. Any JPEG, at the end of the day, is just a file on your hard drive, or an attachment in an email, and a file is just a pattern of zeros and ones. But what does it mean to be a JPEG? What does it mean to be a Word document or an Excel file? Well, generally, some human or some company decided that a file that is a JPEG shall always start with the same few bits, the same pattern of bits. Or maybe equivalently, a JPEG shall always end at the end of the file with the same pattern of bits. Or with something like an Excel file. Like there is something that Microsoft decided, that they decided how to represent rows, how to represent columns in the file. And the only way you can write software that reads Excel files is if you read the documentation Microsoft wrote, so you know how to interpret zeros and ones, right? Remember, everything is context sensitive. In another context, these zeros and ones might be like a secret message written in ASCII, if you interpret these as ASCII codes. But if you open this instead in Photoshop or something, maybe those same zeros and ones are presented as an image. But it turns out then, if you open a file that is of type JPEG, so like something.jpg, Zamaila.jpg, the first 3 bytes of that file, by definition of a JPEG, per its documentation, per the Wikipedia page, are that the first 3 bytes, or the first 8 plus 8 plus 8, 24 bits, should be these 3 numbers in decimal. 255, 216, and 255. Those are going to be zeros and ones at the end of the day, but it's annoying to look at zeros and ones. Decimal's a little more familiar. So it's these 3 bytes start every JPEG. Now, it turns out in the world of files, which again will be one of the domains for the coming week, people don't really use decimal just because, and people definitely don't use binary because it's just way too hard for humans to wrap their minds around typically. They instead use something called hexadecimal, which is a little weird looking, but you've probably seen it in various contexts. Hexa means 16 in this case, and you have literally 16 characters in this alphabet, 0 through 9, and when you can't count higher than 9, you go to A, B, C, D, E, F. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. A is 10, B is 11, ... F is 15. And so that's hexadecimal. But it's the same idea. If we could do the whole columns in 1's place and 16's place and so forth, same idea as week 0, but we have a different alphabet. Now, just so you've seen it, particularly for the coming week's problems, know that those 3 bytes, 255, 216, and 255, in binary happen to be this. Now, what's nice about hexadecimal is that each of those characters, 0 through 9 and A through F, technically represent 4 bits. Why 4? Well, long story short, if you have 4 bits, that's this many patterns. 2 times 2 times 2 times 2. That's 16, ergo hexadecimal. So long story short, hexadecimal is just super convenient because you can take 8 bits or a byte and separate them into 2 hexadecimal values, each of which is 4 bits. So with that said, how do I represent these? 1, 1, 1, 1, I said is 15. And again, if we do the week 0 math, 1, 1, 1, 1 will equal 15 or F. Meanwhile, 1, 1, 0, 1 will equal D. And 1, 0, 0, 0 per week 0 is 8, and so forth. So this is just a very sort of methodical way of taking decimal and sort of presenting it instead as hexadecimal. And humans decided years ago that it's not always obvious when you're looking at hexadecimal that it is hexadecimal. So humans decided that anytime we humans write something in hexadecimal, we're usually going to prefix it, whatever we're writing, with 0x, just because. It's like a visual cue to, hey, human, here comes hexadecimal. So with that said, these now are the first 3 bytes of any JPEG in a file. This is relevant because among the problems for the coming week are going to be this. We are going to give you what's generally thought of as a forensic image, like a copy of a digital camera's memory card on which are 50 photographs, all of which have somehow been accidentally or maybe deliberately deleted. But it turns out, because each of those 50 photographs are all JPEGs, and therefore all of them start with the same pattern of bytes, if you have a mechanism for reading over that file zeros and ones, 1 byte at a time, you could notice, ooh, I just saw FFD8FF. This is probably the start of one of the 50 lost photographs. Let me actually extract that and a whole bunch of bytes afterward and save them to a temporary file. And the next time I see this pattern, ooh, maybe that's the second photograph that's been lost on the digital camera. Let me write that out to a file. And so among the coming challenges is going to be to reintroduce you to JPEGs and have you recover 50 photographs that might have been accidentally or deliberately deleted. But there's other graphical file formats in the world. And one of the earliest common ones was Bitmap, BMP. And as the name suggests, it's kind of a perfect name for a graphic file because it's a bitmap, a map of bits, like the ones and zeros that composed Zamaila's black and white happy face just a moment ago. With the bitmap file format, you might be familiar if you ran Windows XP for some time. If you grew up with like this loading up on your screen, this was a bitmap file called a wallpaper more generally. And bitmaps clearly are supportive of color, some number of bits per pixel. And what's nice about bitmaps is that they're a relatively simple file format. And I say relative because you'll see there's some complexity, but they're way simpler than JPEGs actually are beyond those 3 known characters. As an aside, I thought it's always fun to take a look at what this beautiful field looks like some 20 years later. That is the same thing that you might have grown up with on your wallpaper instead now. But here is, at first glance overwhelming, but in the problem set more methodically presented, what's an example of a file structure. So what does it mean to be a file? At the end of the day, every file on your computer is just a thing containing zeros and ones. But again, those zeros and ones are laid out in patterns. JPEGs, for instance, start with 255, 216, 255. Microsoft Word files, Excel files, anything else is going to start with different patterns as well. And this is the formal way from Microsoft's own documentation for what a bitmap file looks like. And we won't dwell on the low-level details here in class, but long story short, this documentation tells us that the first couple of bytes are something called a word, and the next few bytes are something called a D word or double word, and so forth. So long story short, if you are an aspiring programmer and you want to write a piece of software that reads and writes, like opens and saves graphic files, you have to read documentation like this and understand in what order you read zeros and ones in, and what order you write them out in. Because if it's just a whole bunch of zeros and ones, you don't know what the heck you're looking at. You need to reference documentation like this to know that, oh, it's a number. Oh, then it's a character. Oh, then it's a whole word. Oh, then it's a bunch of red pixels or green pixels or blue pixels. And indeed, if you look at the bottom here, what's nice enough about this file format is that once you go through some of these header fields, as they're called, more on that in the problem itself, you get to something a little more familiar. If you grew up ever hearing the expression RGB, red, green, blue, using those 3 colors, you can combine them, like waves of light, or paint, if you will, into any number of colors of the rainbow by mixing in a little bit of red, a lot of blue, no green, just like we did a few days back when we looked at that weird representation of yellow in the context of a graphics program. But what's in a bitmap file at the end of the day, wonderfully, is a whole bunch of RGB triples. which essentially say top left pixel in a screen will be this amount of red, this amount of green, this amount of blue. Then next in the file is whatever the color is for the second pixel, and then the third pixel, and then the fourth pixel, like essentially a row, a row, a row that compose the actual image. And it's a little fancier than that, but that's the essence. It's a whole bunch of bits that represent some color of the rainbow. But unfortunately, we don't have in C any way of dealing with a structure like this because all we have are arrays, right? We have no data type called file yet until today. So it turns out that there is a keyword in C called struct. And as the name suggests, it gives structure to data. And indeed, one of my claims at the start of today was we want to eventually have data structures in our toolkit. Arrays are not sufficiently powerful to solve real interesting problems real effectively. So it turns out there is no data type in C for the notion of a student. Right? There's ints, and there's floats, and there's chars, and there's kind of sort of strings, but apparently not even those exist. Those are just char stars. But wouldn't it be nice if implementing a piece of software that your friends can use online or that the registrar used to register students, you actually could declare your own data type called students? And indeed, you can. And over the course of this problem set and others, we'll be introduced syntax like this. There's a keyword called typedef and struct that together let you invent, just like in Scratch, your own puzzle piece or your own data type here called student in this case. And as you may imagine, a student might have associated with him or her a name and a dorm, and probably other fields too. But this is a way of inventing your own data type, calling it something very reasonable and sort of obvious to you, and including inside of it, or encapsulating inside of it, two other known data types, like 2 strings, or 2 integers, or 10 integers, or any number of other things. And so simply by using this syntax now can we build up things that aren't just arrays, but have sort of more meaningful data types associated with them, all of which are going to be grouped together. And among the things you'll see in problem set 4 moving forward in its problems is an ability to not only declare data structures like this, but also read them from disk, like read them from files, and then write them to files as well. And indeed, what you'll do in one of the examples as well is manipulate bitmap files, take one as input, and then resize it. Make it much bigger, but scale it all proportionally. Or maybe shrink it. And if you shrink it, kind of figure out what information you throw away and what information you actually retain. And in one third problem still, whodunit, you'll be presented with an image with a whole lot of random noise, a lot of red speckles, much like you might have seen in like a child's puzzle book years ago. And only if, in the real world, if you hold up one of those like red cellophane pieces of plastic, can you kind of see the magic image behind it, you'll implement the notion of that red filter to reveal whodunit in the context of that example. But I thought we'd end today not only with that teaser, but with also this reassurance that perhaps certain shows get these kinds of details more right than others.
Magnify that death spear. Why is it still blurry?
That's all the resolution we have. Making it bigger doesn't make it clearer.
It does on CSI Miami.
All right, that's it for Lecture 4. We will see you next time.